that they don't come to class, even with the recording, it will still be pretty difficult to follow.
And I just started overthinking it, just trying to complicate the situation. You know? I was like, what the fuck are we doing? And I'm like, man, I only have like 2 hours before class.
Alrighty. So are you guys all done with the subtractor?
More or less.
More or less. More or less. What do you mean by more or less?
It was around like 90%. I don't know.
All right.
All the way.
You ever take a letter grade?
Alright, so let me just do one thing, just to double check. I think I got everything. Yeah. So it's basically the same thing as what I had earlier. Alright. Is anyone finding the subtractor significantly harder compared to the adder?
It's about the same.
About the same. Yeah, I don't think it's any more difficult. You know, it's about the same. So once you know how to get the adder working, the subtractor is kind of the same thing. You just have to be careful because of the negation. You just have to be careful. I mean, that's basically all that you have to do. All right. So I don't have a new homework assignment for. Oh yes, I do. Oh, okay. I almost forgot. Yes, you have a new homework assignment. What's the point? Oh, very good. Okay, I like that question. So let's get to the homework assignment, and then I'll explain the significance of the homework assignment because I can't find it yet. Okay, do you have a question for me?
No, just
Okay.
talking about what we did this week.
Okay.
Yeah.
So let's get to the class. All right, so where is my homework assignment? Music box, I forgot to turn it on, that's why. Okay, so I'll show you what the homework assignment is. Okay, so the homework assignment is for you guys to make a music box. Not literally a music box, but the music box that we talked about last time. Basically a mechanism that can automatically change its state just using a clock input. How many people still remember the random 7-segment display thing that I did last time? Mm-hmm. It's basically the same thing, except for 2 things. One, you don't want to display gibberish. I want yours to actually display A to F, and then back to A. So it has to go in a cycle, A, B, C, D, E, F, A, B, C, D, E, F. But the timing has to be even. It cannot be A, B, C, D, E, F, 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 A, B, C, D, E, F, F, F. Okay? It has to be even timing. And that's about it. So you can copy the design that I did last week on last Thursday. For the most part, you just have to add a little bit to it and you're all done. So I'll just go ahead and explain the whole thing. So I want you to make a music box mechanism in Logic Sim, which I did last in the previous class. So the music box is the most basic form of automation. Basically, you're playing a script in an automatic way. The what is essentially is a self-playing mechanism. We did that already. That replaces content of some kind of memory. In this case, we'll use a ROM module, which I also used in the previous class. So the content does not reset upon power cycling. In Logic Sim, all it takes to run the music box is to enter simulation mode and have a clock, quote unquote, tick at a certain frequency and watch the mechanism work. So for those of you who do not recall what I did, or what we all did on last Thursday, let's go to my channel and check it out. So we go to my channel, go to videos, and it's the cisp310 from 4 days ago. And okay, this is the kind of pretty close. Then I attached a 7-segment display to it. Where did I actually finish the connection? Oh, then I talk about how to decode it. How do you fix? Oh, there we go. There we go. So this is close to what you have to do, except you have to do two additional things. You just have to make it go from the letter A to the letter F, and then it has to go back to the letter A. Now, that seems pretty easy, but it's not. The first part is you want to write the letters A to F, but only using a 7-segment display. Okay, so how do you do that? I can't really show that easily. Well, I'm thinking about how to do it with a text editor. I think I can do it. Okay, so let's, because this is using a fixed size font already, so I think I can do it. So an A is pretty easy, okay? So A would look like this. Okay, so we have a bar, another line here. Okay, that's A. 7-segment display, that's basically the best you can do using 7-segment. Or do you guys want me to draw it on the whiteboard because it's just easier on the whiteboard too? Whiteboard? Yep.
So we can't use the hexadecimal digit display?
Nope, it's, what do you mean?
There's one of those in Logisims.
No, you have to use the 7-segment display.
It looks kind of similar. If you want to see. So that's what it would look like.
But how many inputs do you have?
Looks like 2.
Now this one is automatically decoding, so you can't use it.
Worth a shot.
Okay, so an A looks like this. Okay, that's uppercase A. A B looks like this. It's lowercase b. Yes, I know if they're not consistent. A C is up to you. If you want to use uppercase C, fine. If you want to use lowercase c, fine as well. Okay. Okay, so C can be like this. Can also be like this. Yep.
So what letter am I drawing?
A, B, C, D, E, F.
Okay, good.
Okay. A D is like that. And E has to be uppercase. And F is that. So I want you to display A, B, C, D, E, F using these 7 segments to approximate. It can be uppercase, can be lowercase, can be a mixture of the two. Are there any questions? So the only flexibility, the only real flexibility is C, because you can either make it a lowercase c or uppercase C. Either one is considered correct. Okay, I don't really care which one you give me. Okay. Yep.
You can make an uppercase B.
Uppercase B? No, an uppercase B looks like an 8.
Well, an A looks like a, I don't know.
Well, could just be an
No,
8.
an A is an A. But a B, if you close it, it becomes an 8.
You should
Like
talk
that.
less.
Yeah, but you cannot do it with a
it's
7.
the same type of thing, you know?
Well, with 7 segment, this is the best we can do.
Uppercase B.
There's no uppercase B. When you look at the motherboard, they come with, some motherboards come with 2 hexadecimal display for people to debug motherboard issues. They use the same type of display. So I did not invent how to use 7 segments to display, lowercase, the letters A to F.
I'm glad it's not a motherboard.
Well, it does exist on here in the exact same format, just as you said before.
Yep,
It was
they're
on
already
the
decoded. Yep. So that would be, that's kind of cheating. Yep. All right. Okay, so that's the first part. Okay, so the first part is you have to figure out which pin on the 7 segment display controls which segment. That's your first thing to do. Okay, first job. Second job is to come up with the ROM content for A, B, C, D, E, F. That's pretty easy, okay, for the most part. The third one is going to be the hardest. Okay, the third one is you can only display 6 of these items, and it has to go back to the first one. Okay. Now let's get back to the video, because I want to show you what we did last time. Okay. So what we did last time was, let me go back to the part where it actually displays. Okay, there we go. All right. So with this one, it does go back to the beginning, but that's only because when you add 1 to 15, it wraps around to 0. Is that okay? Because the adder and the register, they only have 4 bits. The output of the register only has 4 bits. And as a result, with only 4 bits, you can only represent 0, 0, 0, 0, which is representing the value 0, to 1111, which is representing the value of 15. What do you get when you add 1 to 15 in base 2? We're using only 4 bits.
0.
You get 0 back, okay? Because it's a number wheel. Remember, when we use fixed number of bits to represent number, you don't get a number line anymore. It becomes a number wheel or number circle because you can only recycle the one of the 16 possible combinations. Are we doing okay so far with that? With your design, it's a little bit more challenging because 6 is not a power of 2. So you cannot rely on the natural way for things to wrap around. Okay? Does everybody understand why you cannot just use the simple circuit that I talked about last time and just say, oh, I can just make the register 3-bit. Well, 3 to the power 2 to the power 3 is 8. So you have 2 extra states that you don't know what to do with. Are we doing okay so far with that? Does everybody understand that? Okay? So you have to think about a mechanism to say, okay, I need to turn the content of the register into 0 before it wraps around. Okay? So where do you look? How do you look for that thing? Where do you start? You look at the registers. You look at the register and you say, how can I make a register turn all the way back to 0? And you look at all the pins, right? And you say, okay, can this pin turn the content of a register back to 0? No. How about this one? 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 Ah, that's the ticket. Okay? So once you identify how a register can turn all the way back to 0, then the next question is, how can the output of the ROM be able to turn a register all the way back to 0? And I will leave that part up to you. Okay, this is the one tricky part where you have to make the connection between the ROM, the output of the ROM, and one of the input pins of a register. Okay? Are we doing okay so far with this? So you might need to look into the pins of a register and then figure out a way to say, oh, when we get to this particular memory content of the ROM, it will somehow trigger the register to go all the way back to 0. Okay? And I think you guys can do it. It's just a matter of checking out the register and making that connection. Are we doing okay so far with that discussion? Okay. I think I can see some submission by the end of the lecture because I can see some expressions here. You're like, yep, I got it. If you don't get it right away, it's okay. It's not a problem, because you have 1 week to work on this. Okay, and I think if you really work on this, it won't take you maybe 30 minutes to get it done. Okay, any questions? No questions? Okay, so I'll leave it up to you guys to work on the music box homework assignment because that will form the missing component of our processor. So I'm not going to continue to talk about the processor any further until that part is done. Then we can go on and continue with the discussion of the processor. So what we'll do today is we'll start on a kind of new topic, which is to talk about how negative values are dealt with when we only have zeros and ones. So it's about signed numbers. And you can see that some of these things are just repetitions of what we have talked about already. We still have subtracting and comparing and adding and stuff like that. But the key of this discussion is no longer how do we add in base 2, how do we subtract in base 2. The big question is how do we represent -5, the quantity of -5, when all you have are just zeros and ones. Okay, so that is the focus of today's lecture. All right. What I'll do is I'm going to redraw the number wheel. because I think the number wheel representation is really helpful. And once again, the reason why we have a number wheel instead of a number line is because given a fixed number of bits, there's a finite number of combinations between zeros and ones, and you can only reuse those combinations over and over again. You don't get a number line, which can go from negative, you can go as far as you want. In this case, we start with 0. And I'm going to use a 4-bit example because I don't want to use even 8-bit requires like 256 slots. So 4-bit is good because we only have 16 slots. So it's enough to illustrate the concept, but not so much that it's difficult to draw in class. Okay, 16 slots. The next one is 0, 0, 0, 1, and I'm just going to put in the key ones here. 2, 3, 4, 5, 6. This is 7. This is 8. This is 9, quote unquote 9, and this one is 15. Do we have any questions about the bit patterns on this number wheel? No questions? Okay. So when you add one, you're rotating a pointer in a clockwise fashion. When you are subtracting one, you are turning the pointer counterclockwise. Are we doing okay so far with that analogy? 0 plus 1 is 1, 1 plus 1 is 2, 2 plus 1 is 3, and so on. So the last item is the one where it wraps around. 15 plus 1 goes back to 0. Okay? Are we doing okay so far with the representation of the number wheel? Subtraction works the same way. I can use this one here as an example. The one before 0, 1, 1, 1 is 0, 1, 1, 0. So when you subtract 1 from 7, you get 6, 5, 4, 3, 2, 1, 0. Is that okay? So using this particular number wheel representation, which bit pattern do you think is the best one to represent the quantity of -1? Just based on the direction of the rotation and which bit pattern it is next to. Which one do you think is the best one to represent -1?
15.
Tell me about the bit pattern.
1, 1, 1, 1.
1, 1, 1, 1. You are correct. This one is the best one to represent the quantity of -1 because it is right next to 0 and it is to the counterclockwise direction to it. So, but hold on a second here. Now we have a problem because we also can represent 15 using 1, 1, 1, 1. So which one is that going to be? Okay, what do you think? I'll give you one example. What is this?
That's a line.
It's a line. Okay, what else?
That's a crooked line.
Okay, it's a straight line just drawn crooked.
Segment.
Hmm?
Segment.
A segment, okay.
Minus sign.
Minus sign, okay, very good.
Dash.
In an English class, what would your professor tell you about this? It can be a few, right? It can be a dash, can be a hyphen. But if you know Chinese characters, this is also one.
Wait, you said English class, not Chinese.
But in a Chinese class, how about that? In a Chinese class, your professor will say this is also the character representing the quantity of 1. Okay? How does this have anything to do with our circle, number circle? Yep.
So if you're trying to represent -1, just put that slash in front of 1, 1, 1.
There's nothing. It's really just 1, 1, 1, 1 as a bit pattern. It's just like this line on the whiteboard. It's just one line, one horizontal line. But how you interpret this one single horizontal line depends on the context. If I provide no context whatsoever, you have no idea of what to see or what to get out of this single line. But in a Chinese class, you look at this and you go like, oh, okay, in this context, it is the character representing the quantity of 1. In an English class, you look at this and you go, okay, it can be a hyphen, can be a dash, depending on the relative length of the line. Okay. In a math class, you see this as a line segment. Okay. So in many other classes, there may be some other alternative to look at, just a horizontal line. Same thing with 1111. 1111 by itself is really literally just 4 binary digits. They're all ones. It may not even be representing any actual quantity. It may be just 4 pixels on a black or white screen that is on at the same time. Well, I mean, it has to be a monochrome monitor, but nonetheless, what these 4 ones are representing is up to whatever is interpreting that particular bit pattern. Are we okay with that concept? Is that okay? All right. So if we choose to look at a bit pattern as a signed number, okay, that's the context, okay? We're looking at a bit pattern as a signed numbers. And let's say we have n bits, okay? We have n bits in a particular signed integer. What are the values that we can represent using n bits? In this case, n equals 4 because we have 4 bits. So using this as an example, can someone come up with a general equation or formula to tell me what is the largest number when I give you n bits to represent signed integers?
2 to the n minus 1.
2 to the power of n. Okay, what is the n? What is the minus 1? Apply to the entire thing or
The
just
whole,
n?
yeah.
Apply to just
No,
n
not
itself?
just n.
Yeah.
No.
No?
No, the other way.
You sure? Like that?
I was sure.
Or this? No, that's the answer. That really is the answer. Think about this, okay? N is 4, right? 2 to the power of 3 is 8. 8 minus 1 is 7. 7 turns out to be the largest value that you can represent when you use 4 bits to represent signed integers. That's correct, okay? So it really is 2 to the power of, in parentheses, n minus 1, close parenthesis, the whole thing minus 1. But this minus 1 here is the tricky part. Why do we have subtract 1? It doesn't make any sense. Because the number wheel is separated into 2 equal parts. One part are non-negative numbers. The other part are negative numbers. You have the same number of bit patterns to represent non-negative numbers, which starts with 0 all the way up to 7. The other 8 representations will represent negative values. Now, of course, a math professor will come to me and correct me right away and say 0 is both. It is positive and negative. In computer science, it is non-negative. Okay? So in computer science, we consider 0 as a non-negative number, despite what your math professor has to say. Is that okay? And that is why we have this minus 1 here. What about the most negative value that we can represent using only n bits? Okay, so let's try to figure this out. This is negative 1, negative 2, negative 3, negative 4, 5, 6, 7. This is representing negative 8. So can you generalize and tell me what is the formula based on the number of bits to compute the most negative value that can be represented?
2 to the n minus 1.
Yep, it's negative 2 to the power of n minus 1. So the range of values that you can represent using only n bits is, on the positive side, it is 2 to the power of negative 1, and then that whole thing minus 1. On the negative side, it is just negative 2 to the power of n minus 1. Is that okay? No? Yep.
Why can't we go to minus negative?
Okay, so you're going to chew up more of the bit representation for positive numbers. Hmm? Because then the math doesn't work out. Okay? So the question is, let's say this is how we do it. Okay? And if you look at the number wheel, this is how we do it. In normal arithmetics, you can do a negation, right? So you can look at any particular value and say, what is the negation of that value? So the negation of 8 is just negative 8. So the question now is, can we take a number, a value, take the negation of that, and we have somehow a way to figure out the bit pattern representing that? Okay, that becomes the next question. Okay, let me give you another way to represent this. What is 8? Well, 8 is not a good number because I cannot represent here. What is 5 minus 2? Well, I can re-express 5 minus 2 as 5 plus negative 2, the negation of 2. Is that okay? Is that making any sense? So that means instead of performing a binary subtraction, which you should really be familiar by now, of the representation of 5 and the representation of 2, I should be able to do this one here, which is taking the negation of 2, whatever bit pattern is representing negative 2, add it to 5, I should still end up with 3. Is that making any sense? Because arithmetically speaking, these two are equivalent. So we want to be able to do this, like to perform or to represent numbers so that that works out. Is that making any sense? Sort of? Okay, so let's go ahead and do an example. Let's just carry out this computation. Yep.
For the computer, is it easier to do the negation?
Sorry?
For the computer, is it easier to understand the
Well,
negation?
we'll find out.
Okay.
Okay, we'll find out. All right, so we want to first compute 5 minus 2 using a binary subtractor. Okay, so we are going to carry out the binary subtraction. 5 is 0, 1, 0, 1 in binary. 2 is 0, 0, 1, 0 in binary. And I'm going to do the same thing that I usually do using a separate row for the borrows. Like so. All right, so we'll just go ahead and work out the math. 1 minus 0 is 1 with no borrow. 1 minus 0 is 1 with no borrow. So since I did not have a borrow in either case, this borrow becomes a 0. 0 minus 1 is a 1 with a borrow. So I put that 1 borrow over there already. 1 minus 0 is a 1. 1 minus 0 is a 1. 1 minus 1 is a 0. Neither subtraction yields a borrow, so there's no borrow on this side. 0 minus 0 is 0. 0 minus 0 is 0. I don't really need it, but I'm just going to put an extra borrow of 0 here because that's what your subtractor needs to do. Are there any questions about that particular binary subtraction? No questions? Is the result making any sense? What is 0, 0, 1, 1 representing using the number wheel representation? 3. 5 minus 2 is 3. That makes sense. What is the representation of negative 2? Okay. Just using the number wheel, we know that 1, 1, 1, 1 is representing negative 1. So if you take another tick on the counterclockwise direction, what is the next one? What is the bit representation here? 1110. Okay, so we are suspecting that 1110 is the right representation of negative 2. So that means if I add 5, the binary representation of 5, to the binary representation of negative 2, I should still end up with a 3. Right? If this is the right way to represent negative 2, then everything should still work out. Let's try it. So we have 0, 1, 0, 1 representing the 5, and I'll just explain what we're doing here. We're trying to do a 5 plus the negation of 2, and we just experimentally found out the representation of negative 2 is probably 1, 1, 1, 0. We don't know for sure, we're just trying this out. Okay. And this is the carry row, and this is the final answer. 1 plus 0 is a 1 1 plus 0 is a 1. Neither gives me a carry of 1, so the carry to the next digit is going to be a 0. 0 plus 1 is a 1. 1 plus 0 is a 1. Neither gives me a carry, so this becomes a 0. 1 plus 1 is a 0 with a carry. 0 plus 0 is a 0. And then on the most significant column, 0 plus 1 is a 1. 1 plus 1 is a 0 with an extra carry. Is it working out? Remember, the result has the same width, has the same number of bits as the input. That one extra carry of 1 is not counted as the result. Okay, that carry bit is just kind of dangling out there. We may have some use of it later, but it is not a part of the result. Is it working out? 5 plus what I think is the representation of -2 is 3. Is that okay? Okay. So now here's the more general question. The more general question is, how do we get 2, which is 0, 0, 1, 0, to become 1, 1, 1, 0? And you can see this is not a bitwise knot, because if it is just a bitwise knot, we should end up with 1, 1, 0, 1, because we flip all the zeros to ones and all the ones to 0. And yet it is close. It is kind of close to negation or bitwise negation, but it's not. That's because we are missing a plus 1. Okay? So this is called 2's complement. Okay, so I'll just write down here. 2's complement, I use C2 to represent 2's complement. The 2's complement of a particular bit pattern X is the negation, the bitwise knot of the bit pattern X, and just add 1 to it. Okay. Let's see if this makes any sense here with the value of 2. The 2's complement, C2, of the representation of 2, which is 0, 0, 1, 0. Let's see what it is. It is the negation of 0, 0, 1, 0 plus 1. And what is the negation, or what is the bitwise knot of 0, 0, 1, 0? It's, well, you just flip all the zeros to ones and all the ones to zeros, right? So it's 1, 1, 0, 1, right? And we have to remember the plus 1. What is 1, 1, 0, 1 plus 1 in binary? 1, 1, 1, 0. Ah, so that seems to work. If I apply 2's complement to 1, 1, 1, 0, what should I get back? Because I claim that the 2's complement is the same thing as an arithmetic negation. So what do you get when you take the negation of -2? You should get 2 back, right? The negation of 2 is 2. The negation of -2 is 2. So let's try that out and see if it works. Okay. So you have the 2's complement, but this time we apply that to the bit pattern that is representing -2. So by definition, this is just a bitwise knot of 1, 1, 1, 0, the whole thing plus 1. What is the bitwise knot of 1, 1, 1, 0? You just flip all the zeros to ones and all the ones to zeros, so what do we get? 0, 0, 0, 1 plus 1. And in binary, what is 0, 0, 0, 1 plus 1? 0, 0, 1, 0. We do get it back. Okay. So 2's complement, which is a bit operation, is doing the same thing as arithmetic negation. That's it. That's the bottom line. Do we have any questions about how negative values are represented? Oh, I want to throw in a trick question here. What do we get when we apply 2's complement to 0? What should we get back? What is the arithmetic negation of 0? 0 itself, right? So when we apply this to 0, 0, 0, 0, I should get back 0, 0, 0. Let's see whether that is the case or not. Okay. So we have the bitwise knot of 0, 0, 0, 0, and add 1 to it. The bitwise NOT of 0, 0, 0, 0 is easy because it is just 1, 1, 1, 1 in base 2. But remember the plus 1. Aha, Tech, you were wrong because we got this number. But hold on a second here. Because that extra 1 is the carry. We only keep the least significant 4 bits, which means I was right to begin with. The 2's complement of 0 is in fact 0. So are there any questions about 2's complement, the operation of 2's complement, which is a bitwise NOT and then a plus 1? No questions about that? All right, well, that makes it pretty easy. Wait, hold on a second here. Let me just get back to the earlier computation. The way we added a negative value is the same thing that we do with any bit pattern. Okay? Did I use any special rules when I perform this particular addition? Remember those rules? 1 plus 1 is of 0 with a carry of 1, that sort of thing? Did I bend the rules to make that happen? No, I did not bend the rules at all. Yep.
Well, you had to know the representation of -2.
Huh?
You had to know the representation of
Aha.
-2.
But that's the only part.
Yeah, that's the only part.
I did not change the way I add. Exactly. So the same adder that you did in the previous homework assignment would also work for signed numbers. In other words, binary addition does not even matter whether you're dealing with signed numbers or not, as long as negative values are using 2's complement to represent. Is that okay? Sort of? Yep, go
So
ahead.
like ALUs don't do subtraction, they just do addition?
They actually do subtraction because they need to know, sometimes we need to know the final borrow flag. Okay? Like in this case, we don't have a borrow flag. Let's go ahead and generate a borrow flag. Okay, it's not difficult. Okay. Okay, so you guys can tell me what this should end up as. Okay, what should be the result of this subtraction in binary? You don't need to tell me the exact bit pattern, but it will be representing what?
1 with a bar of 1.
No. If I go through this subtraction, okay, if I go through this actual subtraction, the result of this binary subtraction should represent the value of -3. Okay, because the first number is a 2, the second number is a 5. 2 minus 5 is -3. Okay, so we'll go ahead and carry out this subtraction. And we are not using any new rules for this subtraction. Okay, it's the same rules that we have used for your homework assignment that's due today. All right, so we'll go ahead and see if we get -3 here. 0 minus 1 is a 1 with a borrow. 1 minus 0 is a 1. 1 minus 0 is a 1. Whoops. There we go. 1 minus 1 is a 0. Whoops. And we don't have a borrow in either case, so the borrow here is a 0. 0 minus 1, once again, is a 1 with a borrow. 1 minus 0 is a 1. 0 minus 0 is a 0. 0 minus 1 is a 1 with an extra borrow. Okay? Let's see if I made a mistake. The question is this particular bit pattern, 1101, representing -3? If you look at the number wheel, okay, what is the next item? This is 1110, and the next one is going to be what? 1101. Because it's just 1 less than the previous one. Okay? But I'm still not convinced that is actually -3. What do I do to make sure that 1101 as a binary number, in fact, is the -3 representation? I can do the 2's complement. Very good. So we can apply 2's complement to this particular bit pattern, and I should get back 0011. Yep, go ahead.
Is the bitwise part of 2's complement, or is bitwise not is that part of the complement?
Yes. Bitwise not by itself is also known as one's complement. So when you add 1 to the result of one's complement, we call that 2's complement. Yep. All right, so let's go ahead and check that, okay? Because I am trying to look at this from different perspectives, and it has to work out from all perspectives in order for this to make sense. So the 2's complement applied to 1101 is once again the bitwise not of the same bit pattern, and then we add 1 to the result of the bitwise not. Bitwise not is easy. We just flip all the bits. So we have 0010 plus 1, which is 0011, and 0011 is 3. Okay, so it all works out, okay, which is great. But the question was a little bit earlier, somebody asked, in the processor, we can just do a 2's complement to a value and then add it instead of doing subtraction, right? So let's see whether there are any differences between doing it this way and doing it the other way, okay? So to do it the other way, I am going to figure out what is the 2's complement of 5. So the 2's complement of 5 is 001. 0101 is 5, so the 2's complement of that is going to be 1010 plus 1. Oops, I did one step and then combine it with the other one, so I've got to do it the long way. 1010 plus 1, and the result is 1011. Okay. So now I'm going to do this 0010 plus 1011. Okay, what do you think is the result? Let's do it step by step. Okay, this is a 1, this is a 1, that's a 0 because neither addition results in the carry. 1 plus 1 is a 0 with a carry. This is going to be a 0 here. 0 plus 0 is a 0. 0 plus 1 is a 1 here. Did I make a mistake? Okay, 0 plus 1 is a 1. Whoops. Yeah. Okay. 1 plus 0 is a 1. And there's no borrow or no carry at the end of this. Okay, so when you look at these two operations, they seem to give you exactly the same result with one minor difference. Okay, let's look at the top one here. The top one is actually using a subtraction and say what is 2 minus 5. Ends up with the representation of -3, which is good because 2 minus 3 is -3. Is that okay? The second method, which is the one at the bottom, is doing the same thing, but doing it by using 2's complement so that we are adding 2 to -5. And we still end up with -3, which is great. But there's one minor difference that is really, really important. One ends up with a borrow, the other one does not end up with a carry. Look at this bit here, and look at this bit here. But Tag, you said that's not really part of the result. We just throw it away. So what is the big deal? The big deal is when you need to compare, that bit becomes empty. Okay? And that's why when you do subtraction in the processor, it doesn't just do a 2's complement with a second number and then perform a normal addition. It actually goes through the mechanism of a subtractor. So I'll explain that later. Okay, there will be a time when that becomes useful. But right now, it doesn't seem to be useful. It seems like if I take the 2's complement of one number and just add it to the first number, it's the same thing as the first number minus the second number. Okay. It seems that way, but later on we'll find out that, oh, that extra borrow flag is actually really useful. So are we still doing okay so far with the representation of negative numbers? Yes? Okay. And are we doing okay with 2's complement, which is the mechanism that we use to do the arithmetic negation of a particular value. That's okay too? Okay, excellent. All right, so just to emphasize the difference between, or the importance to separate a bit pattern from the interpretation of the bit pattern. Let's take a look at the bit pattern here. So let's take a look at 0, 1, 1, 0, 1, 0, 1, 0. Okay, we'll just take a look at this particular 8-bit bit pattern. Can someone tell me what it is? Once again, this is a trick question because I did not tell you the context. What am I doing with this particular bit pattern? Am I trying to print something at the printer? Am I trying to display something on the screen? Or am I trying to add something? What am I doing with this bit pattern? If I don't tell you, 0, 1, 1, 0, 1, 0, 1, 0 is really just what it is. It is really just literally 0, 1, 1, 0, 1, 0, 1, 0. But what if I send this particular bit pattern to a printer? What do you think the printer? Well, okay, let's say this is a really old printer. It's only capable of printing text. So what do you think that printer is going to look at this? How is the printer going to look at this particular byte? Yep.
Does the printer have an ASCII table or not?
That's a good question. Okay, so assuming the printer understands ASCII, then it will look at this particular bit pattern and say, oh, this is a bit pattern representing a character, right? So let's look up the ASCII table and find out what this particular bit pattern is representing. Okay, this is the ASCII table. And the ASCII table does not have a column corresponding to binary. Oh, wow. Okay, what do we do now? We change it, and which base do you want to change it to?
X.
Hexadecimal, very good. So this is a 6A, okay? So we look at the ASCII table and find out what is a 6A. And according to the ASCII table, 6A is, oh, it's on the other side. 6A is right here. It is representing lowercase j. So when you send this particular bit pattern to an ASCII printer, it will print lowercase j. But that's not even a number, because it is not in a context to consider this as a numerical value. It is just a bit pattern representing a character. Is that okay? But you guys remember that I said, assuming the printer is an ASCII printer, because ASCII is not the only way to encode characters. What is the other way to encode the characters? Sorry?
Unicode.
Unicode is based on ASCII, so if you look at UTF-8, it is the same as ASCII. What is the other way? Well, if you ask IBM, IBM will say ABCDIC. Okay? So just for the sake of this argument, we are going to look up ABCDIC and find out what is 6A in ABCDIC. E, B, C, D, ABCDIC. Okay, there we go. I like Google. It read my mind.
For when you don't know how to spell it, Google does.
Exactly. And I can probably just say it too. You know, it would just say, "Oh, ABCDIC,"
Into your phone.
and it would actually, you know, use voice synthesis to tell me what ABCDIC is. Okay, this is ABCDIC. Okay, it is a very archaic way to encode stuff. Okay, because just look at the name. Just look at how archaic the name is. Extended binary coded decimal interchange code. What does decimal have anything to do with representing letters and punctuations? Well, it does not, and that's where the extended comes from. So BCD, B binary coded decimal, is the original, you know, form, and then they added extended and interchange code so that they can also use this to represent letters. But remember our main task here. The main task is to find out what is 6A. So we'll look at the table here, absolute table, blah, 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 blah. Okay, okay, so we have 6 as the most significant hexadecimal digit, and then A being the least significant hexadecimal digit. So A is here. So 6A is representing the vertical bar. So the same bit pattern, 0, 1, 1, 0, 1, 0, 1, 0, if you send it to the wrong printer, it's going to print a vertical bar instead of a lowercase j. And I think that really helps to illustrate a bit pattern is really just a bit pattern until you use it for something. So until you add something, you don't have to worry, is this a signed number or not? We don't care, okay? It's just a binary number. Until you do a subtraction, we don't care either. But you know what? I just lied. Because even when you add, you don't care. Even when you subtract, you don't care. Because it's the same adder. It's the same subtractor. Is that part okay? Because when we went through that exercise, went through all of the exercise earlier to try different ways of adding a negative value to a positive value, we did not bend the rules at all. We did not change the rules at all. It's still the same binary adder and the same binary subtractor that we have been using all along. Yeah.
So like theoretically, like you can take that bit pattern, another bit pattern up to a bitwise adder, and then have that lookup table grab some other character.
If you add the ASCII code of one character to the ASCII code of another character, it doesn't really make a lot of sense because the characters, there's nothing really to add. I mean, you can perform the addition, but the resultant value is just a number. It may not even be a character that you can print. Okay, so if the sign, whether a number is a signed number or not, does not matter all this time, when does it matter? When do you think?
Unsigned.
Hmm?
Unsigned.
Well, in C and C++ programming, when do you think signed versus unsigned makes a difference? It doesn't make a difference when you're assigning values, right? When you say, x equals 5 or x equals -5, it doesn't really matter. When you add, it doesn't matter. When you subtract, it doesn't matter. When does it matter?
Variable type, from 0 to whatever instead of minus.
Sorry? When you compare. Very good. Okay, the answer is when you compare. Okay, so let's go ahead and check out why that is the case. And the best tool, well, I think the best tool to do this is GDB. What? GDB? Yes, GDB. So we want GDB to tell me the result of certain types of comparisons. Okay, we'll start off with something that's simple. Print 1 is greater than 2. Okay, it's false. 1 is not greater than 2. Fine. Okay, let's try something else. Print -2 is less than -3. It's false because -1 is not less than -3. Okay, so what is the big deal? But we can force the interpretation of a bit pattern. Okay? First of all, let's see what is really -1. Okay? How can we tell what is the binary bit pattern of -1? We just attach /b. Okay? What /b is saying, what it is telling GDB is, print the following value in binary. Okay? What do you think you will see? And by the way, this is a 32-bit, this is a 64-bit version of GDB. So when I say print /b, which means print in binary -1, what do you think we should be seeing? 64 ones. Okay? Well, I think that's the answer. I'm not really sure. I have never tried this before. Okay. Size letters are meaningless in print command. I'm pretty sure it does. I just need to know how to do it. Say help.
I tried this with a calculator, just in Windows, binary calculator, and it actually does that in there.
Okay.
you put like a negative.
Okay, so it can print in format. Oh, I think I know why. Because it's not B, I think it's T. There we go. Anyone cares to count the number of ones?
64, right?
Okay, so if I don't want to count the number of ones, what is the alternative? Instead of printing in binary, what should I print so I can easily count the number of digits?
Hex.
Hexadecimal, very good. And hexadecimal is X.
It's 32.
I'm pretty sure about that one. And what should we see, by the way?
A bunch of Ds.
It should be all Fs, but how many Fs are we talking about? 64 bits. Each hexadecimal digit is representing 4 bits. 64 divided by 4 is 16. So we should be seeing 16 Fs here, okay? But it's easy to count. Nope. Did I do my math wrong?
I believe it's 8.
I think
That's
you have,
8.
I think you have 32 in there
Yeah.
instead of 64.
So it's only dealing with 32-bit numbers. Did I use the wrong virtual machine? The wrong?
It's entirely possible.
Nope, it's 64-bit.
Mm.
So an int is still only 32-bit wide. Okay.
Do a long round.
Okay, this will confirm it. Yeah, that's why. Okay. Because the size of operator tells you the number of bytes used by a particular type, and int is the default type when you use literal constants. So it's making sense. Okay, so integers are by default 32-bit wide, even though we're using a 64-bit system. Okay, is that okay so far? But what you just said was 1111, 32 ones is really just a bit pattern, right? But when you compare, you have to tell the environment, can be the compiler, can be GDB, you have to say how to interpret 32 ones. Why? You have to say whether it's signed or unsigned. Right?
So it means 2 things.
Because it can be both. It can be, well, it cannot be both at the same time, but it can be either one. There are 2 ways to interpret all ones. It can be -1, can be 2 billion, negative, can be -1 or positive 4 billion something. Okay? So the first thing we'll do is to force GDB to say, oh, don't look at -1 as -1. Look at it as an unsigned number. Now, using what you already know in C and C++, how do we do that? I want to print the decimal version of the largest unsigned integer that can be represented using 32 bits. How do I do that? Okay, so we start with something that we know already. We know -1 is all ones. Okay? But if you just say print -1, it will just tell you, hey, -1 is -1. Because -1 is implying this is a signed number. Okay? So it's automatically interpreting 32 ones as a binary number as a signed number, and there's a -1. So what do you do to change and tell the compiler and say, I want you to look at this as an unsigned number? Yep.
Can you specify to print as an unsigned?
Yes, and that operator is called a what?
I don't know, this is GDB, you're the expert.
I'm the expert, yes. But you're supposed to have passed C, C++ with a C or better. So what is this operator? Unsigned in parentheses is actually a C, C++ operator. It has a particular name. What is it? Typecast. Okay, it's a typecast operator. So this way, I'm casting it, and I'm saying, okay, do not look at the bit pattern of -1 as a signed number. I'm forcing the compiler, or GDB in this case, to look at the bit pattern of -1 as an unsigned number. Press the Enter key, and I have 4 billion something. Is that okay?
4
Billion something.
Oh.
Yeah, if you count the number of digits, there should be 10 digits. So that means you have 4 followed by 9 digits, which is 4 billion something. I can never really remember the exact number. But I can remember stop at 2 to the power of 16. Okay, so if that is the case, then we can do something that's funny. Okay, so we can say, tell me whether -1 is less than 0. Yes, it is. Tell me whether the unsigned interpretation of the binary bit pattern of -1 is less than 0. What do you think? This one is a little tricky. I really don't know the answer. The reason why I don't know the answer is because with this comparison, one side, the left-hand side, is unsigned. The right-hand side, which is just a literal 0, is actually signed. So I really don't know whether it will default to unsigned or whether it will default to signed. So to make sure it will look at it as an unsigned comparison, I am going to be safe. Well, there are two ways to do it, but this is one way to do it.
Might give you a segmentation fault.
Oh, no, no, no. We are not quite at that point where we'll see segmentation fault just yet. Okay? It says it's false. But that makes sense because the unsigned interpretation of -1 or the binary bit pattern of -1 is 4 billion something. Is 4 billion something less than 0? No, it's not. Is that okay? But this is where it makes a difference, is when you compare. Then it makes a difference whether the values should be treated as signed or unsigned. Yes?
Can you take that cast off for 0?
Sure. We'll take it off and see whether it defaults back to signed. And that's a good question. I think it will follow whatever the left-hand side is. So this will give me the same result. Yep. Because from the perspective of a compiler, which parses from left to right, then it will just say, oh, the left-hand side is already of this type. So when it sees the right-hand side, which is different, it will coerce the right-hand side automatically to the same representation. But this is not a good test, okay? Because
we could do -2 is less than
-2 is a better one.
-1.
-2. No,
We'll do unsigned on the right.
you coerce one to be unsigned, and then you put a -1 on the other side. Okay. Let's do it without a coercion first, or without a typecast first. Can someone tell me what is the expected answer of this question? Is it true or false? 1 is less than -1. Should be false. Okay, fine. Okay, that's good. It is false. And then we put a typecast on this side, on the left-hand side. So my own experience of writing compilers tells me that when the compiler parses from left to right, it would have seen the left-hand side being an unsigned type first. And when it encounters the right-hand side, which is signed, it will coerce, which means it will do the typecasting automatically and silently without telling you. So that would basically be comparing 4 billion on the right-hand side with 1 on the left-hand side. So the answer to this question should be true. No, it should be true. Because it's going to cast the -1 to unsigned also. It's called coercion. It's automatic.
What is 1 less than 1?
1 is less than 1 is false. Because 1 equals 1.
So if it changes the -1 to 1.
No, that's not what it's going to do. It's going to change the interpretation of the representation of -1 to unsigned.
4 billion. Which is the 4 billion?
Which is the 4 billion something. So it essentially will be comparing 1 to 4 billion something. So that's what I'm thinking it should do, okay? Just because of my own experience with writing compilers. Yep, that's what it is. It's not really necessarily a good thing when you can think like a compiler. Some people can call it a mental condition.
When
That's
you're
what
writing your
happens
code.
when you are dealing with that sort of thing for decades. Okay, but are there any questions about this? Are you guys getting this part? Which is kind of not related to assembly language programming, but it's sort of related to representation. Yes. Okay. Yep.
So what is the treatment to this mental condition?
You choose a career that is suitable.
No, I mean like what kind of I don't know, like statements would you need to say in order to, you know, have what you want?
Just
Does
have
that
to
make
try
sense?
and avoid comparing unsigned integers with
Like what things,
regular ones.
what things would you need to watch out for when you're making your if statements or whatnot?
Oh, okay.
Yeah, it's not
I thought you
like-
were asking about my mental condition of thinking like a compiler.
No, I'm asking
Okay.
about the thing. It's reference. Come on.
Okay, so with this, you have to think like a compiler. You really don't have a choice. I mean, if you want to find out what the code is going to do, you have to do one of the two things. One, you can try to think like a compiler, which will get you right most of the time. Or you can look up the documentation in C and C++ and find out whether the left-hand side type will determine the right-hand side interpretation in a situation like this. Okay. Okay, let me give you an example in an actual C program. I know this is a little bit out of the context of this class, but it does relate to what we are talking about. So I'm going to go to the temp folder, create a program called CMP for compare. This is just a regular C program. And we have this. And then we have int x unsigned y. Okay, so these are variables. And I'll do the same thing. Y has a value of 1. X has a value of -1. But remember, up to this point, whether x and y are signed or not is completely pointless. Because the assignment operation is not sign sensitive. 1 is simply specifying 31 zeros and a 1. -1 is simply specifying 31 ones, or 32 ones. It's just a bit pattern specification. Is that okay? What really is going to matter is the next one. Okay, so the next one, I'm going to say int result. Okay, I'm going to store the result of the comparison. So I can say result equals to the same thing that I did earlier. I have the y, which is an unsigned number on the left-hand side, and the signed -1 on the other side, which is x here. Okay? And that's the entire program. So when I compile this program and run it in GDB, result should get back the same thing that we got earlier, which is true, which is a 1, non-zero. Yep.
Should we display it as well? Make sure.
No, we
that
can
was
use GDB to look at result.
Oh, yeah, that's fine.
All right, so we're gonna compile this program, GCC dash, I can do a warn all. It will just nag me about certain things, but it's not gonna be incorrect. Okay. See, it complains that result has a value initialized, but it is not used, okay? Which is not a bad thing, it's just, you know, kind of awkward. Then I can GDB, oh, I forgot a dash G, sorry. Let's apply a dash G here to include debug information. There we go. So now I can GDB CMP, list the program, put a breakpoint on line 10, run the program. Now I'm on line 10, which means result has a value in it. So this is the moment of truth, because if the C compiler is going to do the same thing as what I did earlier, what I reasoned out earlier, result should be non-zero or 0?
Non-zero.
Should be non-zero. Okay. And it is non-zero. But the behavior of the C compiler is dictated by ANSI C standard. So somewhere, you know, buried in the ANSI or ISO, you know, standard of C and C++, they probably specify if the left-hand side and the right-hand side has exactly the same width, then the left-hand side signedness determines the right-hand side signedness as well. Okay. All right. But it's a comparison. But we haven't talked about comparison. But we did talk about something that is related to comparison. What do you think is related to comparison? How do you compare? If I give you two choices, addition or subtraction, which one do you think relates to comparison?
Subtraction.
Subtraction. Okay, so we'll take a look at subtraction.
String compare.
And interestingly, the first thing we'll do is deal with unsigned subtraction. So we'll first deal with unsigned comparison, which is done by subtraction. Okay, we have done a few examples already, but let's go ahead and focus on a few additional examples. Okay, and we'll take a look at we'll compare 15 to 1. Okay, so the question is 15, is it greater than 1, less than 1, or equal to 1? Okay, so we'll do the subtraction. This one is easy, right? 15 is what as 4 bits. How do you represent 15 in 4 bits? All ones. Okay, so we have 1 1 1 1 minus 0 0 0 1. I mean, you don't really have to go through all the calculations. You guys already know the answer, but we'll go ahead and do this. Okay, 1 minus 1 is a 0. 0 minus 0 is a 0. There's no borrow here. 1 minus 0 is a 1. 1 minus 0 is a 1. No borrow. Okay, the rest is pretty much the same thing.
So is it the carry that determines whether it's greater than or less
Yep,
than?
exactly. It's the borrow.
What determines if it's equal to?
Aha! Okay, let's check out what is equal to. Okay, so that's okay. That's I'm not gonna give you any results here. So we'll flip it around and say what is 1 minus 15. So you're getting it. You're getting to the core of the issue here. Okay. All right. So let's figure this one out. 1 minus 1 is a 0. 0 minus 0 is a 0. No borrow. 0 minus 1 is a 1 with a borrow. 1 minus 0 is a 1. 0 minus 1 is 1 with a borrow. 1 minus 1 is a 0. Again, 0 minus 1 is 1 with a borrow. 1 minus 1 is a 0. Okay, so this one we do end up with a borrow. Okay, and then we'll do a 1 1 1 1 minus 1 1 1 1 because they are the same. Okay, so we just need one like that just to be complete. Okay, I don't think we need to really explain this one. Oops. Unless I make a mistake. Because they're all going to be zeros. Okay. With no borrow. Okay. Alright, so just from looking at this, the final dangling borrow that's hanging out there, what do you think that indicates? If the borrow flag is a 1, what is it telling you?
It's a sign number.
Okay, what is the relationship between the first number, the top, and the bottom?
Top is less than bottom.
The top is less than the bottom. Exactly. That's the only thing you can conclude. Okay. Now, what if the borrow flag is a 0? Then what can you conclude? Yeah, the top number is not less than the second number. That's all you can say. They can be equal. Okay, so you're not guaranteed that the top number is greater than the second number or the bottom number. You can only tell that. You can only say it's not less than. That's all you can conclude. Okay, so the borrow flag is useful this way, and that is why when you subtract numbers, you cannot just do a 2's complement on the second number and add, because then it won't set the borrow flag the way it should be. That's why subtraction is a separate circuit in the processor. It is not just 2's complement and the addition circuit. It has to be a separate circuit. Okay, what about signed comparison? This is unsigned comparison. Pretty easy. Does it make sense? What is that final borrow flag actually representing? What is this borrow representing? Okay, the top number is, okay, I'm gonna pick on somebody here, pick on somebody that I know. bad thing is I cannot remember names of people. Okay, what's your name? Brian. Okay. So the top number is how much money I have, and the second number is how much Brian is trying to collect from me. Okay? So in that case, what do you think its borrow is representing? Whether I have to go to the bank or not, right? But what do I do at the bank? So I got $1 in my pocket. Brian comes to me and say, hey, Jack, you owe me $50. I want it now. What do I do? Well, Brian's getting his money. Brian's getting all $15 that he is asking for. But what do I have to do? What is this one representing? I go to the bank and borrow something, right? How much am I borrowing? $16. Okay, I'm borrowing $16. And it makes perfect sense because I already have $1 in my pocket. I borrow $16 because this digit, this column, would have represented the number of 16s on the number, right? Because this is 1, 2, 4, 8, that's 16. So I go to the bank and the bank says, I can only loan money in powers of 2. I can loan you $1, $2, $4, $8, $16, and so on. And they go like, well, I don't need $32, I just need 16. So I get $16 from the bank plus the one in my pocket, I got $17. Out of the $17, I give you 15 that I owe you. So I end up with $2 back. I end up with $2 in my pocket. But when do I not have to go to the bank? When I have more money than Ryan is asking. Okay? And these are all unsigned. Okay? So that's why in an unsigned comparison, if the borrow flag is a 1, it means the second number is bigger than the first number. Is that okay? But when you look at this as a signed number, then we have all kinds of trouble. Okay? So let's see what the time is. We have 2 more minutes. So with 2 more minutes, I cannot explain signed comparison. What flags can we use to indicate whether one number is less than another number in signed comparison? There's not enough time to do that, but the notes, we'll talk about that. But what I can do is to talk about, but how do we know 2 numbers are exactly the same? Because the borrow flag itself cannot indicate that. The borrow flag being a 0 simply means the first number is greater than or equal to the second number. So by itself, I cannot say, oh, is it greater than or is it equal to? It doesn't tell me. So when you look at the addition thing, okay, so this is going back to what you guys are doing, ABC minus DEF, and we'll just call the result XYZ. XYZ are the 3 bits of the results, okay? How can you tell that ABC as a bit pattern represents exactly the same value as DEF? What would be the characteristics of XYZ?
0, 0, 0. They
all have to be zeros, okay? But I don't like to think in an active low or inverted manner. So how do we look at XYZ and say, okay, I want a formula that is a 1, but only if XYZ are all zeros?
Not X and Y and Z.
Exactly. So not X and Y and Z is called the 0 flag. The 0 flag is the negation of, no, that's not true. Okay, I take it back. It is the OR. It's the negated OR. Okay, the 0 flag is the negated of the disjunction of the 3 bits or all the bits of the results. Does that make any sense? Because if the result is non-zero, then at least one of XYZ is a 1. But if at least one of XYZ is a 1, the disjunction is going to be a 1. The negation of 1 is a 0, which means it is non-zero. If ABC and DEF are exactly the same, then X, Y, and Z, they're all going to be zeros at the same time. The disjunction of a bunch of zeros is a 0. The negation of a 0 is a 1, which means it is, in fact, 0. So this is the formula to compute what we call the Z flag or the 0 flag.
did Morgan's law apply to that?
We don't have to, well, if you want to, you can apply De Morgan's law. If you apply De Morgan's law, this
Not
whole
X
thing
and
just
not
becomes
Y.
not X and not Y and not Z. Same thing. It makes sense as well, okay, because you want all of these to be zeros in order for the Z flag to be 1. So I only have enough time to explain the Z flag, which is fairly easy. One question. Does it matter whether the numbers are signed or not when you want to know whether they are the same or not?
No.
It is sign insensitive, okay? So next time we'll focus on how we compare signed numbers. Because that's when the tricky part comes in, because no one single flag can tell you the result. You have to combine 2 flags to do it. And don't forget your current homework assignment, which is the music box. You know, you might want to go back to the notes from the last Thursday. You know, start with that. You know, just kind of play around with the 7-segment display a little bit and be done with it.
Doesn't seem too bad.
No, it should not be too bad.